Hello, my name is Ashish and I will be the course instructor for reverse engineering with Ghidra. Before starting, I would like to give an introduction about myself. So, I am a security researcher who likes to work with low-level security and learn about Windows internals. I also play CTFs during my free time. I have experience with finding vulnerabilities in ICS SCADA systems, and I have also published research paper regarding to that. I have worked at Smokescreen Technologies to build endpoint deception agent, and from that I have gained a lot of experience about Windows internals. This module will give an introduction about the x86-64-bit assembly, in which we will cover Windows and Linux calling convention, stack organization, function Prolog and Epilog, how the segmentation works in 32-bit systems and 64-bit systems, and we will look at how loops works in assembly. So Ghidra, as we all know, is a software reverse engineering framework which is developed by NSA. It has analysis tool for analyzing compiled code on a variety of platforms including Windows, Mac OS, and Linux. It supports a variety of processor instruction sets and executable formats. Currently, it only supports the static analyzer, but the debugger to perform dynamic analysis is promised to be released in future. Now, what is reverse engineering? Reverse engineering can be applied in different aspects of software as well as hardware development activities. In the context of software engineering, reverse engineering entails taking a software program's binary code and recreate it so as to trace it back to the original source code. It is used to fix certain bugs in software as well as to enhance product features in both hardware and software. The main reasons for reverse engineering are to audit the security, take away the copy protection, modify the embedded systems, as well as include additional features, not having to spend much alongside related activities. The main reason for reverse engineering are to audit the security, take away the copy protection, modify the embedded system, or include additional features into the software. Reverse engineering is used in software design to enable the programmer or developer to incorporate new features into the existing software. It is used by developers and testers to understand the inner workings of their program. It is used by security researchers and malware analysts to ensure that the system lacks any major security flaws or vulnerability. It can be used by exploit developers to take advantage of a bug or vulnerability in order to cause unintended behavior to occur on computer software or hardware. Such behavior frequently includes things like gaining control of a computer system, privilege escalation, or denial of service attack. To perform reverse engineering, we must first understand how the compilation process takes place within an operating system. C and C++ are compiled languages, so that it has to be compiled into machine code. C source files are a convention named with .c extension, and we can use GCC or WinGW to compile the C source file. The first step that the source code goes through is the pre-processing stage. In this stage, the preprocessor obeys commands that begin with hash. The preprocessor starts by removing the comments, expanding the macros, and expanding the included files. So if we have included a header file such as stdio.h, it will look into the stdio.h file and copy the header file into the source code file. The preprocessor also generates macro code and replaces symbolic constants defined using #define and their values. Compilation is the second step. It takes the output of the preprocessor and generates assembly language. The assembly language is human-readable language which is specific to the target processor. Assembly is the third stage of compilation. The assembler will convert the assembly code into pure binary code or machine code. This code is also known as object code. In the last and final stage, linking merges all the object code from multiple modules into a single one. If we are using a function from libraries, linker will link our code with that library function code. There are two types of linking. In static linking, the linker makes a copy of all used library functions into the executable file, whereas in dynamic linking, the code is not copied. It is done just by placing the name of the library in the binary file, and at last we get our executable file. To perform reverse engineering of such an executable, we have to pass the executable through a disassembler or a decompiler. A disassembler is a computer program that translates machine code into assembly language, the inverse operation of that of an assembler. A disassembler differs from a decompiler, which targets a high-level language rather than an assembly language. Disassembly, the output of a disassembler, is often formatted for human creativity in code writing process. Decompilers are different from disassemblers in one very important aspect. While both generate human readable text, decompilers generate much higher level text, which is more concise and much easier to read. There are two parts in reverse engineering process. One is called the static analysis and another one is dynamic analysis. Static analysis is done in a non-runtime environment, which is just when the program is not running at all. So any kind of static analysis tool that is used will look at the code and will look at the runtime behaviors to find any kind of flaws, backdoor, or bad code. In contrast, dynamic analysis is done just when the program is running. A dynamic test will monitor system memory, function behavior, response time, and overall performance of the system. We also look at how the values in the registers get changed and what is their value at a particular memory location when the program is running. When doing malware analysis, we can load the executable into a disassembler such as Ghidra to perform the static analysis. The machine executable code can be converted into assembly language so that it can be easily understood by humans. In dynamic analysis, a debugger can be used to determine the functionality of the malware executable, which otherwise would have been difficult to obtain using other techniques. Unlike static analysis, it is behavior based, so it is hard to miss important behaviors. As we can see here, it is the assembly listing view which is available inside of Ghidra. We can use this listing view to perform our static analysis. For dynamic analysis, we can use tools like GDB, WinDebug, or x86-64 debug. GDB is only available inside of Linux operating systems, while WinDebug and x86-64 debug is available only on Windows. The data type in a programming language is a collection of data with values having fixed meaning as well as characteristics. Some of them are integer, floating point, character, etc. Usually, programming languages specify the range values for given data type. In assembly language, 8 bits comprises of a byte and 16 bits is called a word. It can also be called as 2 byte. 2 words constitutes of a double word and 2 double words constitutes of a quad word. In a 64-bit operating system, register RAX is available of size 64 bits. In 64-bit operating system, all registers can be accessed in 16-bit as well as 32-bit modes. In 16-bit mode, the register is identified by its 2-letter abbreviation. In 32-bit mode, this 2-letter abbreviation is prefixed by E, which means extended. For example, EAX register is the accumulator register as a 32-bit value. Similarly, in 64-bit version, the E is replaced by R, which means register. So the 64-bit version of EAX is RAX. It is also possible to address the registers AX, CX, DX and BX in their size of 16 bits as 2 8-bit halves. The least significant bit or low half is identified by replacing the X with L. The most significant byte or high half uses the H instead. For example, as we can see from the diagram, AX is divided into 2 high part and low part called AH and AL. We will have a look at how these registers get used, and we will look at the calling conventions in Linux as well as Windows. An instruction set refers to the set of instructions that a compatible microprocessor supports. These instructions are usually part of an executable program, often stored as a computer file and executed on the processor. The x86 instruction set has been extended several times, introducing wider registers and data types as well as new functionalities. If we have a look at common opcodes that are used in Intel-based microprocessors, they are move instruction, which moves the value from memory and registers. There is a push and pop instruction that are available, which we can use to add a value to the top of the stack or remove a value from the top of the stack. We have compare instruction to compare two values. Then there are bitwise operations like AND, OR, XOR or NOT, and we can also shift the bits using logical shift or arithmetic shift. To understand these instructions better, let's have a look at some of the examples. In the first example, move EAX X5. You can pause the video and try to guess an answer what this instruction does. It moves the immediate value 5 into register EAX. In the second instruction, move EBX EAX, it moves the value from the register EAX to register EBX. Move ECX hex 1337 in close bracket moves the value from the address hex 1337 to register ECX. Move EDX EAX plus EBX into 4 moves the value from that address to register EDX. LEA EAX, EAX plus EBX plus 1, 2, 3, 4, 5, 6. To find out what this instruction does is the LEA abbreviation stands for Load Effective Address. It loads the address of the location reference by the source operand to the destination operand. It moves the affected address from EBX into 4 into register EAX. The biggest reason that you can use LEA over move is if you need to perform arithmetic on the registers that you are using to calculate the address. Effectively, you can perform that amount of pointer arithmetic on several of the registers in combination effectively for free. Another important feature of the LEA instruction is that it does not alter the condition codes such as carry flag or zero flag while computing the address by arithmetic instructions like add or multiplication does. This feature decreases the level of dependency among instructions and thus makes room for further optimization by the compiler or hardware scheduler. Next instruction, jump x1337, is an unconditional jump to address x1337. Jump if equal to, jump if not equal to, or jump if greater than equal to x1337 is a conditional jump to address to that address. We will have a look at conditional and unconditional jumps when we will learn about loops in assembly. The x86 architecture has 8 general purpose registers, 6 segment registers, 1 flag register, and an instruction pointer. The 8 general purpose registers are the accumulator register used in arithmetic operations, counter register used in shift rotate instructions and loops, data register used in arithmetic operations and input-output operations, base register used as a pointer to data, stack pointer register points to the top of the stack, stack base pointer register used to point to the base of the stack, source index register used as a pointer to a source in stream operations, and the destination index register used as a pointer to the destination in stream operations. The 6 segment registers are the stack segment, which is a pointer to the stack, code segment which points to the code, data segment which points to the data segment, extra segment which points to data, where the E stands for extra, FS segment register points to the extra segment, and G segment register, GS, points to still more extra segment. Most applications on modern operating systems like FreeBSD, Linux, Microsoft Windows use a memory model that points nearly all segment register to the same place and uses paging instead, effectively disabling their use. Typically, the use of FS and GS is an exception to this rule, instead being used to point to the thread-specific data. The E flags register is a 32-bit register used as a collection of bits representing Boolean values to store the results of operations and state of the processor. The different use of these flags are carry flag, parity flag, adjust flag, zero flag, interrupt flag, and so on. When we have a look at 32-bit Linux calling convention, we see how parameters are passed to the function, in which EBX to register EBP contains the 6 arguments, and EAX contains the syscall number. Whereas if we have a look at 32-bit Windows calling convention, it is divided into many calling conventions like fast call, STD call, or CDCL, etc. In the fast call calling convention, when we have a look at this example in which we are passing parameters 5 and 6 to function 1, the parameters are passed in EDX and ECX register, and a call instruction is used to call function 1. In CDECL calling convention, we use the same example to pass parameters 5 and 6 to function 1. But we see here that the parameters 5 and 6 are passed by pushing the variables onto the stack. The 64-bit operating systems add 8 more general purpose registers named R8, R9, R10 and so on up to R15. The 64-bit architecture also includes SSE2, so each 64-bit CPU has at least 8 registers named XMM02, XMM7 that are 128-bit wide but only accessible through SSE instruction. The Linux and other POSIX operating system follow the official System 5 AMD64 API calling convention, in which the first argument is passed in RDI, second in RSI, third in RDX, and fourth up to sixth in R9. Then stack can be used to pass the parameters. The RAX register contains the return value from that function. Register R8 to R9 are volatile register and base pointer as stack pointer are non-volatile. The 64-bit calling convention in Windows is a little bit different from the official System 5 AMD64 API. There is no more CDECL, STD call, this call, register calling convention. In Windows 64, there is just one native calling convention, and modifiers like CDECL are ignored by the compiler. This reduction in calling convention helps in debugging the code better. The 4 arguments are passed in register RCX, RDX, R8 and R9, and the return value is in register RAX. Register R10 and R11 must be preserved by the caller, and R12 to R15 must be preserved by the callee. The RBP register is used as a frame pointer, and RSP register is the stack pointer. A memory management unit transforms a logical address into linear address by means of a hardware circuit called as segmentation unit. Subsequently, a second hardware circuit called a paging unit transforms the linear address into a physical address. Starting with the 80286 model, Intel microprocessor perform address translation into 2 different ways called real mode and protected mode. Real mode exists mostly to maintain processor compatibility with older models and to allow the operating system to bootstrap. Each logical address consists of a segment and an offset that denotes the distance from the start of the segment to the actual address. A logical address consists of 2 parts, a segment identifier and an offset that specify the relative address within the segment. The segment identifier is a 16-bit field called the segment selector, while the offset is a 32-bit field. For any program execution to take place, at least the code segment, data segment, and stacked segment must be loaded within a valid segment selector. The extra registers ES, FS, and GS are freely available to use. Every segment register has a visible portion as well as an invisible portion. The visible portion of the segment registers are manipulated by the programs as if they were simply 16-bit registers, and the invisible portion are manipulated by the processor. A segment selector is a 16-bit field in which 13 bits are used as an index which selects one of the 8192 descriptors in GDT or LDT. 1-bit indicator flag specifies the descriptor table to use. Requester privilege level specifies the current privilege level of the CPU when the corresponding segment selector is loaded into the CS register. It also may be used to selectively weaken the processor privilege level when accessing data segments. The CS register has another important function. It includes a 2-bit field that specifies the current privilege level of the CPU. The value 0 denotes the highest privilege level, while the value 3 denotes the lowest one. Linux uses only level 0 and level 3, which are respectively called kernel mode and user mode. Each segment descriptor is represented by an 8-byte segment descriptor which describes the segment characteristics. The segment descriptors are stored either in global descriptor table or in local descriptor table. Usually only one GDT is defined, while each process is permitted to have its own LDT if it needs to create additional segments besides those created in GDT. The address and size of the GDT is in main memory are contained in GDTR control register, while the address and size of the currently used LDT is contained in LDTR control register. The translation from logical address to linear address is done using the segmentation unit, which examines the TI field in the segment selector to determine which descriptor table is used, whether it is GDT or LDT. Then it computes the address of the segment descriptor from the index field of the segment selector. The index field is multiplied by 8 and the result is added to the content of GDTR or LDTR register. It then adds the offset of the logical address to the base address field of the segment descriptor, thus obtaining the linear address. In 64-bit operating system, the architecture does not use segmentation in long mode. The 4 segment registers called CS, SS, DS and ES are forced to 0, but registers FS and GS can still have non-zero base address. In Windows, the GS segment register points to the thread environment block, and in Linux, the GS and FS registers are used as thread local storage and canary-based stack protector within a program. Let us now discuss how stack works when we execute a program. The stack is a last in first out data structure in which data is pushed onto it and popped off of it in the reverse order. The stack is usually to pass the arguments to function or procedures and also to keep track of control flow when the call instruction is used. The other common use of stack is to temporarily saving registers. In Intel-based CPUs, the stack grows from higher addresses to lower addresses. We will have a look at in-depth organization of the stack within a program when we debug a program using GDB in the next module. In assembly language, the function Prolog is a few lines of code at the beginning of the function which prepares the stack and registers for use within the function. Similarly, the function Epilog appears at the end of the function and restores the stack and registers to the state they were in before the function was called. The function Prolog and Epilog also sometimes contain code for buffer overflow protection. The function Prolog typically performs the following action. It pushes the current base pointer onto the stack so it can be restored later. It assigns the value of stack pointer to the base pointer so that a new stack frame can be created on top of the old stack frame. It moves the stack pointer further by decreasing or increasing its value, depending on whether the stack grows up or down. On x86, the stack pointer is decreased to make room for the function's local variables. Function Epilog reverses the action of the function Prolog and returns control to the calling function. It typically does the following actions. It drops the stack pointer to the base pointer, so room reserved for the function Prolog for local variables is freed. It pops the base pointer off the stack, so it is restored to its original value before the Prolog. It returns to the calling function by popping the previous frame program counter off the stack and jumping to it. The x86 processor contains a built-in instruction which performs the part of Prolog and Epilog. To perform the action of Prolog, the enter instruction is used, and to perform the part of Epilog, the leave instruction is used. A function may contain multiple epilogs. Every function exit point must either jump to a common epilog at the end or contain its own epilog. Therefore, programmers or compilers often use the combination of leave and return to exit the function at any point. Conditional execution in assembly language is accomplished by several looping and branching instructions. These instructions can change the flow of control in a program. There are two types of conditional execution. One is called the unconditional jump and second is called the conditional jump. The unconditional jump is usually performed by using the JMP instruction. Conditional execution often involves a transfer of control to the address of an instruction that does not follow the currently executing instruction. Transfer of control may be forward to execute a new set of instructions or backward to re-execute the same steps. In conditional jump, it is performed by using the J and the condition, depending upon the condition. In case of conditional jump, the conditional instructions transfer the control by breaking the sequential flow, and they do it by changing the offset value in instruction pointer. The conditional jump is often preceded by a compare instruction. The CMP instruction compares two operands. It basically used in conditional execution. This instruction basically subtracts one operand from the other for comparing whether the operands are equal or not. It does not disturb the destination or source operand. It is used along with the conditional jump instruction for decision making. If we have a look at the while loop, in which we have a condition and a body, the corresponding translation to the assembly language, we can see that we are using a CMP instruction to check the condition, and then it is followed by a conditional jump which exists out of the while loop if the condition check fails. If not, the unconditional jump jumps to the while body and continues to loop within the body. The JMP instruction provides a label name where the flow of control is transferred immediately. As we can see, the JMP instruction is followed by a label called while body. It jumps to the while body and loops within it. If some specified condition is satisfied in conditional jump, the control flow is transferred to a target instruction. There are numerous conditional jump instructions depending upon the condition and the data. For example, JE, which stands for jump equal, JNE, which stands for jump if not equal, etc. Let's have a look at how for loops works within an assembly. We see that the sum is of data type int, which is assigned a value 0, and I is instantiated with value 10. The corresponding assembly is that the sum is in var 8, which is assigned value 0, and var 14 contains the value I, which is 10. The for loop then performs the addition of variables sum and I and checks the condition of whether I is greater than 0 or not. If the condition is met, then it loops within the for loop. It does a unconditional jump to the for loop. The CMP instruction compares that if the value of I is greater than 0 or not. If this comparison succeeds, if this condition succeeds, then it does an unconditional jump to the for loop, and if the condition becomes false, it exits out of the loop. The JMP instruction can also be used for implementing loops. For example, the following code snippet can be used for executing the loop body 10 times. The processor instruction set, however, includes a group of loop instructions for implementing iteration. The basic loop instruction has the following syntax of loop and the label, where the label is the target label that identifies the target instruction, as in the jump instruction. The loop instruction assumes that the ECX register contains the loop count. When the loop instruction is executed, the ECX register is decremented and the control jumps to the target label, while the ECX register value, that is the counter, reaches the value 0. We will be ending this module here, and in the next module we will be setting the lab environment for using Ghidra, in which we will analyze both Linux and Windows executables. We will learn about the basics of GDB and see how shared and dynamic linking works. That's all for today. Thank you and have a nice day.